Hello, everyone. Welcome. I'm delighted to have with us Professor Shu Han, who is an associate professor of bridge engineering at Tongji University. He was previously a postdoc at Texas A&M, and he received both his bachelor's and master's degrees at Tongji University. In 2016, he joined the research group of Dan Frangopol, leading figure in lifecycle engineering, to pursue a PhD degree at Lehigh University. His research interests include lifecycle management for structures and infrastructure systems, community resilience analysis, reliability algorithms, among others. He received the Alfred Nobel Prize in 2024 in recognition of his research work on lifecycle management for bridge networks. Thank you, Professor Han, for doing this. He's going to talk about community resilience analysis using the agent-based modeling approach. All yours, Professor Han.
Okay, thank you, Pranay, for the introduction, and thank you, Pranay Minghui, for inviting me. And this is indeed a great honor for me to be a speaker for this seminar. And today, my topic is community resilience analysis using the agent-based modeling approach. And this will be a flowchart of my presentation. First, a brief talk about my motivation, and then I will introduce the concept of agent-based modeling, and then I will introduce the test bed I'm using for the agent-based modeling, and then some results for the tornado resilience analysis. And next is a verification and validation process will be conducted on the resilience analysis result. After that, community resilience will be conducted for another hazard, which is seismic hazard. And finally is the conclusion part. Okay, for the motivation, actually, the motivation for doing community resilience analysis is quite self-evident. And we have seen multiple figures like this, which shows that the frequency of occurrence of natural hazard is in general on the rise. And this is the return period of hazards across United States. And in America, there are multiple very hazard-prone regions. And of course, hazards can lead to significant consequences. The economic losses can be tremendous, and the recovery period can be long. And during the long period of recovery, some negative things can happen, such as joblessness and homelessness. So, community resilience is certainly a very important research topic. And this is the concept of resilience in the official document. And so basically the concept of resilience put an emphasis on the ability to withstand and recover rapidly from disruptions. The second part is about the introduction of the agent-based modeling. There are certainly a lot of modeling approaches for resilience analysis. Among those approaches, agent-based modeling is perhaps the most detailed, and perhaps the most powerful modeling approach. An agent-based model is a computational model for simulating the actions and interactions of autonomous agents. There are certainly many theories behind the agent-based model, and a great strength of agent-based modeling is that it is suitable for modeling the complex behavior of interconnected infrastructures. It is good at modeling complex systems. And when we do agent-based modeling, we simulate the behavior of different types of agents at a macro level. But simulating this behavior, we aggregate the macro level interactions into macro level responses of the entire system. So we can make the observation of the entire community, the entire system. And these are some illustrations of agent-based model. So basically, agent-based models, in an agent-based model, agents are created representing the real-world physical entities. And an agent certainly needs to interact with environment as well as with other agents. And for the creation of an agent needs to have some attributes and need to have the behavior. For example, let's say we create an agent for a person. This person has the age of a person may be considered as an attribute. And how a person goes to work, whether by bike, by public transportation, or driving a car, it is the behavior of a person. If I remember it correctly, the history of agent-based modeling dates back to 1980s. I think maybe it was started by some national lab in US. Yeah. But now agent-based modeling have widespread applications. It is applied in different areas such as construction management, financial market, traffic simulation, and epidemiology. Okay, this figure shows what a community consists of. A community is regarded as a system of systems. So there are different systems in a community. For example, the electric power network, which is about and the power and the water supply network. These are the utility systems. And the community has households and schools and businesses and maybe also government, which is the administration, which is an administrative system. And when we do community resilience analysis, we are certainly interested in how to apply hazard mitigation strategies, and it certainly involves decision making. We will see, let's say we have several options, several hazard mitigation policies. We need to determine which policy should be applied and which policy is the most effective one. And when the resources to repair is of limited supply, how to allocate the limited amount of resources. That also involves decision making. And this figure shows the more detailed interactions among different systems in a community. For example, for the households or a household agent, because the children in a household need to go to school, so a household agent will certainly have an interaction with a school agent. And the adults in a household needs to go to work. So a household will also have interaction with businesses. And as I mentioned previously, a strength of agent-based modeling lies in its ability to model the interactions between different systems. And of course, there are some within each part, within each system, there are also models that need to be applied to model the recovery process of the system within itself. And this slide shows a list of agents created for this research. We certainly need hazard modeling, which means we need to create a hazard agent. And I already mentioned a lot of agents. And there are some agents that are created to facilitate the recovery process, to facilitate the modeling. For example, we need construction company agent to facilitate the repair process of some important damaged structures, like damaged schools. And this slide shows a more detailed recovery process of school agents. And when a tornado occurs or some other hazards occurs, first we need to do a fragility analysis to determine the damaged states of educational institutions. And here, for the damaged state, the Jesus Convention was adopted, in which I think 4 different level of damage states are used. Like DS1 is slight damage, DS2 moderate damage, DS3 extensive damage, DS4 complete damage. Based on the damage state, the education system or the schools go through the recovery process, and of course for minor damage, for the schools with that minor damage, it will recover quickly. But if the school is completely damaged, it may need a long time to recover. And the students originally enrolled in complete is created for handling the repair process, and when a hazard occurs, I'm sorry, can you hear me? I think the
Yes.
Yeah, it's fine.
Okay,
There
okay,
was a
okay,
slight
fine.
delay. That's no longer the case, so it should work.
Okay, thank you. Yeah. And yeah, so when tornado or other hazards occurs, all the damaged structures will send a repair request. So basically, there is a queue of repair requests, and the construction construction company agent will handle this repair queue and allocate the repair resources. And yeah, so of course, because there is a queue, I think you can set up some priorities. Otherwise, the repair is done. I mean, like first come, first serve. And this is the recovery for the household agent. And of course, some models need to be adopted to simulate the recovery process of a household. And here we use the Markov chain model proposed by these two scholars to update the housing stages of a household. And when a household is the structure is damaged, the residential structure is damaged, and there are 4 stages defined by these two scholars, like from emergency shelter to permanent housing. And I would like to mention that actually these are the research today. What I present is the research I did when I was a postdoc at Texas A&M. And yeah, so at Texas A&M, I joined the research group of Professor Maria Colio. And I'm not the first one in her research group to work on agent-based model. So previously, prior to me, one of her PhD student, Mohammed Agababe, he actually some work are done by him. So he proposes like 10 housing status. This housing status can reflect the status of household more precisely. And of course, the link between the 4 stages and these 10 status are defined by Agababe. And these slides shows the recovery of functionality of business agents. And basically, the recovery of businesses have 2 aspects. One is the structure, whether the structure of businesses has recovered. The other is whether the business have enough employees to run the business. And for the structural damage, there will be a recovery state chart, flow chart. And after the structure is repaired, the business needs some licensing, needs some approval to reopen. But after it's reopened, it may not have enough employees. And so the hire process will begin, and the business function will be complete when it has both enough employees and the structure of business is intact. So, and here we categorize the skill level of workers into 3 categories, like low skill, high skill, medium skill. And so actually it's related to the job updating process of the workers, which I will talk about soon. And for the person agents, actually in the community we consider each individual as an agent, and and we basically look at 2 important processes. One is the medical treatment process for people if they become injured, And the second is the occupation, the job updating process. So a business can lay off its employees if it is not functioning, and the people that are out of work can apply for a new business and can apply for a new job. It's based on their skills, level of skills, and their business category. And for the medical treatment residential buildings, the buildings they live in, and all the data are based on the Jesus manual. And for the job updating, the job updating is conducted periodically, and while whether a person can send out a job application hinges on his ability, if this person has the ability to work, and there are multiple criteria for the ability to work, like the health condition, and whether this person is forced outside the city because of the housing status change, or whether this person has responsibilities to take care of someone, like the children that are out of school, or maybe the family member become injured and he need to take care of the family members. So anyway, and also if a person is out of job and has the ability to work, he will send out job application request and be placed in a labor pool. And there is an agent called unemployed labor pool agent to handle the job application process. And these are for the hospital agent. And first, I would like to mention that in each system, we need to define the functionality of each system, because to calculate the resilience of a community, we need to get the resilience of each system first. And to calculate the resilience of each system, we need to define the functionality of the system, because the resilience is calculated as basically the average functionality over a certain period of time. Sometimes we call it control time. And for hospital, I think I consider the functionality in two aspects. The first is the medical care treatment. Yes, the level of the quality of treatment. The other is like the availability of medical resources, such as the emergency beds and inpatient beds. And this figure, the figure on the right-hand side, shows the medical care treatment process. When an injured person arrives, a triage will begin. And if it is determined that this person needs treatment at the hospital, he will be placed in a waiting queue for the emergency beds. And if he can get an emergency bed, he will receive the treatment. And if it is determined in the emergency beds that this person needs further medical care, then he will queue for the inpatient beds and receive a further service. Okay, previously I mentioned that I'm not the first person in Professor Colliel's research group to work on agent-based model. So yes, Mohammed Akbabe is the first one in her research group, and he built the agent-based model using a commercial software called AnyLogic. So it is a proprietary software, which means that it's not free. But it certainly has its advantages. It has a user-friendly graphic interface. Basically, you can just build the model by clicking the mouse in the interface. And for the creation of the agents, each agent will have its own interface where you can define multiple processes. For each process, you can lay out a state chart like the one on the right-hand side. And I think this one is for the recovery of the residential of the households. And when so the damage estimation will be conducted on the residential structures. If the residential structure is damaged, then it will assume an initial housing stage, and then the Markov process will begin. The stage updating will be conducted periodically. And when I joined Professor Colio's research group, she would like me to create the Python, create the agent-based model not using any logic, but using Python package. Because there are certainly advantages in using any logic, but using any, if I use, there are certain also disadvantages. For example, if you use any logic, you just click the mouse, build the interface, but you do not know what's hidden behind the interface. You do not know the codes behind this state chart. So if I write the code in Python, everything is very clear, and it can become an open source model. So I take on that task. Of course, I cannot start from scratch. I need to use some established Python packages. There are some specialized Python packages for agent-based modeling. For example, like MESA and AgentPy. And in our case, we can use a more simple Python package because here we are, for our research, we only consider the recovery in the time domain. We track the recovery over a certain period of time. And we don't do some like modeling of spatial analysis, like how the traffic moves like during after the disaster happens. So in this case, we can just use some discrete event simulation package to do the agent-based modeling. So I choose this Python package called SimPy. And of course, I need to have a Python environment to write the code. And so I use Anaconda software. And of course, in the Python model, in the agent-based model, I also need a Python package to handle the fragility analysis because damage assessment is also necessary. And I use a Python package called InCore. It is developed by the NIST Center of Excellence. I think it's headquartered in Colorado State University. Okay, the third part is about the test bed. So for the application of agent-based modeling, a total of 2 test beds are selected. One is called center view, the other is called Joplin. The first one, center view, it is actually a virtual test bed, which means that it does not exist in real world. It's designed by some scholars. And it is supposed to located in Midwestern US. And it is in a suburban area. And here also you can see some detailed statistics like the population in Centerville. For the Joplin, it's a different story. Joplin testbed represents the real city of Joplin in Missouri State. And this city experienced an EF5 scale tornado in May 2011. And it is in a metropolitan area, which means that it has more buildings, more businesses, more education institutions. So you can see the spatial layout of these 2 test beds. On the on the left-hand side is the you can see there are different zones in Centerville. Some are residential zones and some are business zones. And on the right-hand side, it is a spatial distribution of buildings. And based on the structural formation and also the resistance to tornado resistance, a total of 19 archetypes are classified for these buildings. And the detailed information of these 19 archetypes is shown in this table. As you can see, archetype 1 to archetype 5 are residential buildings. while the rest of the archetypes are for non-residential buildings. Okay, now I will talk about some details of the tornado resilience. And of course, for the community resilience analysis, hazard modeling is also very important. And for the tornado, we need to determine the wind field. And because for Centerville, it is a virtual test bed, so we need to apply some theoretical tornado models, a theoretical wind field. So here I use this multi-layer rectangular shape wind field. It is, I think, designed by scholars in also the NIST Center of Excellence. And this is multi-layer rectangle, and the smallest rectangle in the middle actually is associated with the highest wind speed. And for the real world, a real test bed of Joplin, I can use the wind field associated with the real world event in May 2011. I think this wind field is determined by some post-hazard reconnaissance work. And both these two wind fields are for EF5 scale tornado, which is the highest scaled tornado. And then I can run, after I create the agent-based model, I can run the simulation, I can run the model. Now, I just, to see some results, this is for one scenario, which means I only run the agent-based model once and see some results. Like the figure on the left-hand side shows the recovery profile of the utility access. You see the people without utility drops to 0 within a relatively short period of time. And also this is like some up and downs for the time variant unemployment rate profile. And there will be a spike and then some up and downs reach a plateau and gradually decreases. And finally, the unemployment rate level will decrease to the pre-hazard level. And this figure shows the time variation of the number of people unable to work due to several reasons. And you can see the people forced outside city is the major reason that people are unable to work. And the figure on the right-hand side shows the time variation of the number of employees that two businesses have over time. And the businesses represented by the yellow curve certainly hit harder compared with the blue curve businesses. And this slide shows the job updating for two persons. Basically, they lost their job and then they got a new job. But the time for get a new job can be different. The time for the first person to be rehired is much shorter than the second one. But so previously the result as for one scenario, just run the model once. But actually in an agent-based model, there are a lot of uncertainties, right? The fragility analysis has uncertainties, the results, damage state has uncertainties. And the recovery time for structure in a specific damage state also has uncertainties. And there are some queuing behavior which also associated with uncertainties. So I need to certainly do a Monte Carlo simulation on the agent-based model, which run the agent-based model multiple times and get a histogram. So these are for example, these are the histogram of the recovery period of education system at different level, elementary levels, middle school level, high school level. And I would like to mention that in this case, I tracked the recovery for 2 years. So actually, you can see the bar is the highest bar is for the 700 days, which means that actually after 2 years, this elementary school system has not recovered. And I just showed some ultimate result, which is the histogram of the resilience indices of different systems. And actually the control time for different systems are different. the utility access are certainly expected to have a shorter control time compared maybe to education system or business system. And finally, for the community resilience, it is in here in our study, we calculated it as the weighted geometric mean of these 5 infrastructure systems. Okay, now there are some results for Joplin. This shows the histogram of the number of damaged buildings, both residential and non-residential. For the sake of comparison, the histogram of damaged buildings in Centerville are also shown here. And basically, because the economic development level of Joplin is higher than Centerville, so which means that there are more buildings in Joplin than Centerville. So when the tornado of a specific scale, there will be more damaged buildings in Joplin than in Centerville. And these are some comparison of recovery profiles for the 2 test beds. And this is for the recovery of utility access, and this is the recovery of the education. Like this is the time variant profile of the number of students that are in normal schooling status, which means that they are not like in a temporary place to receive education or need to find a host school. So for the utility, actually, so I think there are more damaged electric utilities in Joplin than in Centerville. But because Joplin is more developed, it has more resources to do the repair. As a result, the recovery profile of the 2 test beds are close to each other. And for the education recovery, well, because there are more education institutions, the students are more spread out in Joplin than in Centerville. So when tornado hits, actually the percentage of students are originally enrolled in damaged schools is lower than the percentage in Centerville. So actually the recovery of the education system in Joplin is faster than Centerville. And this slide shows the distribution of households in different stages. So you can see that even for an EF5 scale tornado, actually the permanent housing stage, which is it indicates which is the stage that a family should have, is like from beginning to end, the dominant type of housing stage. And the 5th part is the verification and validation of the education. Of the results. Oh, sorry. So whenever we got some result from a model, we need to ask ourselves if the result we have are reliable or not. So we need to do verification and validation. So the concept of verification is to make sure that the model is programmed correctly, and no mistake have made in the model implementation. And in this case, what I focused on the verification, in terms of the verification, is that whether the theme Python package I use is reliable for handling the discrete event simulation. Because for any logic software, it is an established software. I consider it as reliable. But I'm not so sure about SimPy, so I need to check whether SimPy is good or not. So how to check that? I can run a simple example problem using the 2 approaches and compare the results. If the results align with each other, then I think SimPy package is good. Otherwise, it is not. So there are a lot of example problems in the user manual. Actually, they are embedded in the software embedded in any logic software. I select an example problem called a calling center. So I will not mention every details of this example problem. Basically, like there are two groups of staff at the calling center. Each group are trained for handling a specific type of call. But because of the uncertainty of the arrival rates of callers, the type 1 caller may be received by type 2 caller, which is not an ideal situation. So anyway, I solve this example problem using two approaches and compare the result. And actually, the result aligns with each other. The error is insignificant, which means that SIMPA is a good package. And for the validation, actually, it's more, I would say, it's more involved. So there are different things that need to be done, and we can do a phase validity, which to see if the result will converge over time. And also we can do some uncertainty quantification for the internal validity. And more importantly, we need to compare the results obtained using two software packages. And this time not for the example problem, but for the community resilience agent-based model. And finally, we can do some parametric analysis using the agent-based model. That is also a validation. Okay, and this slide shows more detailed explanation of the phase validity. Like I can check, of course, I also need to check whether the program can run, and also whether the result can accurately, realistically represent the recovery process. And basically, I need to check if the result will stabilize, if it converge. You can see basically it will all the result will converge, right? And also I need to check whether some results are reasonable or not. For example, like whether whether the recovery period of some systems is reasonable, right? If the recovery period for school is only like 10 seconds, that's perhaps not reasonable, right? If it is 100 years, that's also not reasonable. So, and also you can see that there will be certainly, I expect some spike in unemployment rate after hazard. So there are some, you just need to take a look at the result and see using your own judgment, right, whether the results are reasonable or not. And of course, I need to compare the result using two approaches, and the alignment is quite good. And these are for the histogram of damaged buildings, I think. Okay, and then this is the sixth part, the seismic resilience, which I will only briefly talk about it, because basically for the seismic resilience is about a different hazard. The hazard modeling is different, right? And I just I do some parametric analysis on two important factors in hazard modeling. One is the location, the coordinate of the epicenter. The other is the depth of the earthquake. And so I investigated the influence of these two parameters on the recovery process and of course the damage state. And I also use INCOR to handle this like the fragility analysis, and also the INCOR can actually handle the entire hazard modeling as long as you specify those parameters. And here shows some result. So basically, in the end, it turns out that for the near, actually for the, so you can see the maximum depth I consider is only 50 kilometer, which means that the earthquake is like a shallow earthquake. The depth is not significant. So for this kind of earthquake, actually the depth is not very significant in terms of the impact on recovery. But actually the recovery or the damage state of the recovery is sensitive to the location of the epicenter. And in this case, I investigated the effect of hazard mitigation strategy on community resilience. And in this case, I consider doing structural retrofits and consider retrofitting different types of structure and compare the resilience with the non-retrofit case. So finally, it's about the conclusion and acknowledgement. And I just list some major conclusions. For example, the level of development of a community certainly will have an impact on its recovery. Like a more developed economy may have a more vulnerable business system because more businesses will be damaged, but it maybe have a stronger resilience in education system. And of course, the spatial layout of structures in a community is important. For example, for tornado hazards, only the structures locating on the path of the tornado is likely to be damaged. And I would like to mention it again that the agent-based modeling is a powerful tool. We can obtain reliable results as long as we have enough information of the agents, and this information should be reliable. And certainly there are maybe some significant future research directions. For example, how to achieve knowledge transfer between the resilience analysis of different test beds. Suppose I have done resilience analysis for multiple test beds. Now, a tornado hits another city. Can I directly make some predictions on the recovery based on the results I have for the previous for several previous test bed, right? Okay, for the acknowledgement, actually the research was mainly supported by this NIST Center of Excellence, the center at Colorado State University, and also the NIST project also contribute to this research, and of course I need to thank the High Performance Research Computing, the HPRC Center at Texas A&M, and without which I cannot run the model because of the computation expense. Okay, and that's it for my presentation. Thank you, and I welcome all the questions.